Welcome to the lecture series on tricks of the trade in deep learning with artificial neural networks. This video covers the weight update step and why it shifts the mean input with rectified linear units. Let's have a look at the update formula of the backpropagation algorithm. We update all weights with this formula that combines the deltas in layer n-1 with the x with the outputs of neurons in layer n-2. So let's look at the red neuron here. This neuron gets input from many neurons from the previous layer, and the updates of the green weight use this delta, but the updates of the red weights also use the same delta. So in that sense, all the weights onto this neuron share the same delta. And now suppose that we use rectified linear units, so the x, the activities of these neurons, the output of these neurons, are either 0 or positive. Let's look at the formula. The delta is the same for all these weights to the same neuron, to the red neuron. The x's are all 0 or positive, so the update steps are of the weights onto the red neuron are either all positive or all negative. It's not possible that one is positive and one is negative. So in that sense, all the weights onto the red neuron increase or decrease together. And this has consequences. For example, let's look at weights with index 5 and index 2. They are both going to the same neuron I in layer n-1. And this is the current situation of the weight vector. And learning will try to make the weight vector move down. However, it's not possible to move down directly because weight updates are either all positive or all negative. They decrease or increase together. So we can do this, then they both go down, and then this, they both go up, they go down, they both go up, they both go down until we go here. So to do something quite simple, so this is a situation where the weight with index 5 would have to go down and the weight with index 2 has to go up, but that's not possible unless we do these iterations of decreases and increases together. This problem is absent for hidden units that have a gain function which has positive and negative values. For example, it's not a problem if we have a transfer function g of a, which is the hyperbolic tangent. Then we would be able to make weight changes directly into the desired direction. So this is a specific problem for ReLUs and other units with non-negative outputs. It's no problem for the hyperbolic tangent, and it's also no problem for other units that cover the space of positive and negative outputs. And one of these examples is the shifted exponential linear unit, also called CELU, that I will discuss next. So the shifted exponential linear unit, the CELU, combines a couple of interesting features. I've sketched it here in black. Similar to the ReLU, it's linear for positive activations. The slope is a bit larger than 1, but it's linear, and that means it doesn't run into the vanishing gradient problem for large activations, in contrast to the hyperbolic tangent. For negative activations, it's not 0, but similar to the hyperbolic tangent, it also covers the range of negative outputs. And in this way, it avoids the bias problem. It doesn't change the mean during the update step. So what is this bias problem? I already discussed this update formula of the weights, which means that if the delta is positive, then it's shared by all neurons J connecting to this neuron I. And if for the ReLU, if these X are all non-negative, then the weights updates all go in the same direction. They are all positive for positive delta, and they are all negative for negative delta. I discussed that this leads to a zigzag for the weight updates, but another implication is this bias problem. Let's look at the mean activation of this neuron I in layer N before the update step. It's given by this formula. Now after the update, we have to add these changes in the weights, but as just discussed, they all have the same sign. So they are all non-negative or all non-positive. So if this xj itself is non-negative for all j, which is the case for the ReLUs, that means that the mean activation changes, the bias changes. But controlling the mean was important as discussed during the initialization of the weights. It was important because if the mean moves out away from zero, then we may run into the vanishing gradient problem for sigmoidal units, or we may run into the linearity problem. So it's important that we keep the mean always roughly in the same regime. And that's why we need units that have positive and negative parts. So let us summarize what I've discussed so far in a little quiz. First statement: a non-zero weight update step of ReLU shifts most often the mean. If you agree, raise your hand now. And yes, this is correct. Second claim: in a network with CELU, there are active units in the forward path which contribute a vanishing gradient in the backward path. Well, think about this. No, this is wrong. So the CELU in that sense behaves just as the ReLU. It inherits the nice properties of the ReLU. Third claim: a non-zero weight update step of CELU shifts most often the mean. If you think that this is true, raise your hand. And this is not true. So the CELU solves the problem that the ReLU has without getting in the problem that you might get with a hyperbolic tangent. So now let's look at the CELU in more detail. The orange curve here shows the CELU, and down here you see the formula. We have a beta larger than 1, which means the slope here is slightly larger than the one of the ReLU. And down here it saturates, but it does not saturate at -1, but it saturates at a slightly at the negative value, which has a slightly larger absolute value. So these parameters, beta and gamma, are chosen such that first, the mean doesn't typically change during an update step. Second, that we don't run into the vanishing gradient problem. And third, that we don't run into the linearity problem in the forward path. Now let's see how a network that contains CELUs as hidden units performs. CELU is now green, the continuous line is training, the dashed line is test error or test accuracy. And what you see is that a network with CELU learns faster. In the end, there is no significant difference between other units. But it learns faster, and it learns faster because the CELU addresses the 3 problems that I have discussed in the 2 previous parts. It addresses the shift of the mean, it addresses the vanishing gradient problem, and it allows to exploit the nonlinearities, which means it addresses the linearity problem in the forward path. So the most common choice in the literature is that you take a ReLU. However, if you are free, I would suggest that you take the CeLU. The initialization of the weights is important in the initial phase of training. The choice of hidden units is also important in the initial phase of training. The ReLU has a disadvantage because it doesn't keep the mean during the update step, and this is why it requires batch normalization, and that's what we are going to discuss in the next part. The hyperbolic tangent as a hidden unit has a problem with the vanishing gradient. The sigmoidal has a problem with vanishing gradient and the shift of the mean, the bias problem. The CeLU solves all these problems and is currently the best choice.